Welcome everyone to lesson 3.13 from Precalculus, which is all about trigonometry and polar coordinates. So we're finally diving into this world of polar, which is very different than anything that we've done before. So let's dive in. Historically, for most of your academic career, you have graphed on the xy plane, which is formed by the x-axis, a horizontal line, meeting the y-axis, a vertical line, intersecting at 90 degrees at intersection point we call the origin. But in 3.3, you found that you could define a point that was in the form of x comma y by using an angle in standard position and the point's distance from the origin. So that way of describing points is called the polar form. And we're going to dive into that in this lesson and the next few lessons. So it's going to get a little bit weird, a little bit interesting, but it's okay. We're just diving in and we'll see where it takes us. So first and foremost, a rectangular form, the old way of doing things, is x comma y, where x is the horizontal distance from the origin, y is the vertical distance from the origin. This is also known as Cartesian. It depends on how much history your teacher really knows or just how particular they are about the definitions and the words you use to describe things. So some teachers are going to use rectangular form. Some teachers may use Cartesian form. They are exactly the same thing. Cartesian comes from a French mathematician, René Descartes, who kind of invented this way of describing solutions to equations as, the lines and curves that we've been using, all from a Frenchman, and we named this way of doing things as x comma y kind of graphing. We've dedicated the name to him. So that's all fine and dandy. Let's talk about the new stuff. So polar form, which is the new thing, describes a point by r comma theta, where r is the radial distance or the true distance from the origin, which we are going to call the pole, and the angle of the ray that the point lies on in standard position. So remember, standard position means that the initial ray is the positive x-axis. So if we look at a polar plane here, we have the pole, which is the old origin, right? And the only axis we have is called the polar axis, and it is only the positive x-axis. So instead of being a line, it is a ray that starts at the pole and then goes forever to the right. Not bad. The weird thing about these points, though, is that it's r comma theta, which is a little interesting because when we start to talk about polar functions, theta is the input and r is the output. So it's the exact opposite of what you have previously experienced, where the input is the first number and the output is the second. For polar, it's the opposite. The output is the first number and the input is the second number. So a little bit different, but again, we're going to ease into that discomfort. We're not going to freak out because it's not too bad. So let's plot some points. That's never that bad, right? So what we're going to do is we are going to look for the ray first. We're going to look for the angle we're going to use, which in this case is pi over 6. So we're going to plot it along this ray here, and the distance from the pole is going to be 2. So I'm going to use these circles to judge that distance. So 1 circle, 2 circles. So our magic point here is right here. Oh, it does not like that for some reason. So our magic point is right here. Not bad. So that's how it works if everything is positive. Makes sense. What if we have something that's negative? So for a negative radius, what we're going to do is we're still going to find that angle. So 7 pi over 6, 1/6 more than a whole pi, is here. A negative radius means instead of going out from the pole on that ray, we're going to follow it back. So in this case, we're going to use this 7 pi over 6. We're going to go through the pole in the opposite direction. And then we're going to go 1, 2, 3. So that point, you could also think, is positive 3 comma pi over 6. And that's right. There's more than one way to describe points in polar, which is kind of interesting. Just like we had coterminal points before, if we have an angle that is larger than 2 pi or less than 0, it's coterminal with something that's between 0 and 2 pi, which I think is really, really cool. Foreshadowing, if we have a negative angle, instead of going the positive way, which is counterclockwise from the polar axis, we're going to go clockwise. So instead of counter, we're going clockwise. 3 pi over 4, so that is right here. This would be this right here. And we want 1, 2, 3, 4. So this would be our point here. So not that bad. Again, we said that we could describe points in multiple ways. There's more than one way to describe these points, so we have to get used to that. Here it wants us to write the polar point in 4 different ways. By that, I'm going to take that as I want positive, 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 negative, negative, positive, and negative, negative, and let's see how that works. So let's keep it simple first, and let's look at the positive, positive case, right? So I can see clearly that the angle is 5 pi over 3, so 5 pi over 3, and the radius is 1, 2, 3, 4. So this is going to be positive 4, 5 pi over 3. Not bad. Let's make the radius negative. So if I use a negative 4, that means that I need to follow this to the opposite side. So following it through the pole to its opposite angle, 1, 2, 3, 4. So we're just using this angle here, but we're going to call it, I was just using that angle there. Woo. So 2 pi over 3. Again, not that bad, right? What if I want a positive 4, but a negative angle? So positive 4, negative angle. So instead of going counterclockwise, we're going to go clockwise to it. So I look at the mirror reflection, right? This mirror reflection would map onto pi over 3. So this is pi over 3 in the negative direction. So this would be negative pi over 3. And now, fanciness, let's go for negative, negative, right? So all of these are going to be 4. So we're going to use a negative 4. So we're trying to get to this ray here. But how do we get there with a negative angle? So we need to look for its mirror reflection. Its mirror reflection is going to be 4 pi over 3, so this would be negative 4 pi over 3. So again, really not that bad. So plotting points, baby stuff, right? But the conversion's where the fun really happens. So in lesson 3.3, we learned about converting these 2 different ways. Whether we realized it at the time or not, and I think I did foreshadow it, we can use this diagram here to really build up our ways of converting. Well, how do I get the y-coordinate using r and theta? Well, y would be r times the sine theta. X would be the r times the cosine theta. How do I get r from x and y? Well, I use Pythagorean's theorem, so I can use r is equal to the square root of x squared plus y squared, or the distance formula, if you know what is that. And I can use tangent to find theta. This is the new one. We really didn't talk about this one at the time in 3.3 because we didn't know about inverse trig at the time. Or we did, but we didn't discuss it yet in a precalculus context. So even though we're using tangent for this, inverse tangent, we remember that inverse tangent is restricted to not the whole circle. So we have to use our trig knowledge to work with it. So we know if we're in quadrant 3, we're going to have a tangent that is going to be positive. We just have to keep that in mind. And so on and so forth for quadrant 2. So just bearing that in mind. So without further ado, let's actually convert. So we have, I'm going to change to green so it's a little easier to see. We have r and we have theta, right? So I know that x, the x-coordinate, is equal to r cosine theta. And I know that the y-coordinate is equal to r sine theta. So let's just plug in what we have. We know the x-coordinate is going to be 6 cosine of pi over 3, comma, and we know that the y is going to be 6 sine of pi over 3. And we're going to use what we know about trig to actually do this. We want exact answers if they give you special angles. We don't want any of the decimal stuff. We're grown-ups here. We can do it. So, again, I draw pictures for these. So I'm going to draw a picture of a triangle in the first quadrant because of the angle, right? So pi over 3. And I know that this is the medium side, so this would be 1 root 3, 2. Cosine would be 1/2, so 6 times 1/2 is 3. And I know that sine would be root 3 over 2, so this should be 6 divided by 2 would be 3, so 3 root 3 would be our point. So again, not bad. This is all stuff kind of we've done this part before, right? We didn't call it what it was, but we've done this before. Doing this one here, again, we know what x and y are, so I'm going to go ahead and write it as a point. So we have 4 cosine of 5 pi over 4, comma, 4 sine of 5 pi over 4. I don't know what this is off the top of my head. I do, but I'm going to feign ignorance here, right? If I don't know what I'm doing, where is 5 pi over 4? 5 pi over 4 is 1/4 more than a whole pi, so that puts it in quadrant 3. So drawing my triangle here, and we have pi over 4 more than pi, right? A quarter more than pi, which means that this would be 1 root 2, or, root 2 over 2 would be what's going on here. We are going left and down, so this is negative and this is negative. Well, that makes it look like a 4. There we go, better. So we have negative root 2 over 2 for both. So this is negative root 2 over 2, this is negative root 2 over 2, which means we're having the 4 in both cases, so we have negative 2 root 2, comma, negative 2 root 2. So not bad. What about the other way? Well, we know that we have r is equal to the square root of x squared plus y squared, and we know that theta is going to be equal to tangent inverse of y over the x. It's the slope, so it's the y over the x, right? All fine and dandy. R, not that hard to do. So r is equal to the square root of negative 3 squared plus 5 squared. So negative 3 squared is 9, 5 squared is 25, 9 plus 25 is 34. So we know that r is equal to the square root of 34. It's not pretty, but we're going to leave it like that because it's prettier like this than it would be as a decimal. Now we need to find the angle. And when we find the angle, we really need to be careful about the quadrant. Negative x, positive y puts us in quadrant 2. Inverse tangent doesn't exist in quadrant 2. But the inverse tangent of negative 5/3 does exist, right? So if I go to my fancy calculator here, make sure I'm in radians, I am. So if we go inverse tangent of negative 5 divided by 3, I do get a number. But that's not the number I want, right? Because this number is in quadrant 4. Not good for us. We don't want quadrant 4, we want quadrant 2. So how do we move it? We're going to add a pi to it. So we're going to take this and we're going to add pi, and this is our angle. So our point is going to be the square root of 34, comma, 2.111. Not great, but you get the idea. Not pretty, but it works. So let's try it again with this one here. So we already know that r is the square root of x squared plus y squared. So r is equal to the square root of 2 squared plus negative 6 squared. 2 squared is 4. Negative 6 squared is 36. So we get 4 plus 36 is 40. So we get the square root of 40. And I don't know how your teacher is, but there is a square in there. 40 is 4 times 10, and I can take the square root of 4. So this is actually 2 root 10, if we want to simplify it, right? Now we can get the tangent. So where are we? What quadrant are we in? Positive x, negative y puts us in quadrant 4. And inverse tangent does exist there, but we're going to see something interesting happen. We want the theta, which is the inverse tangent of -6/2. You could put -3. That's perfectly fine if your brain already went to that. So if we do inverse tangent, so second tangent, -3, we get this. Now, we can have negative angles, but if you're on a multiple choice part of an exam or something like that, my assumption would be is that they would use something between 0 and 2 pi. So how do I get this back to between 0 and 2 pi? I add 2 pi to it. So I'm going to add 2 pi. And that gives me the radians. So our point would be 2 root 10, comma, 5.034. Not bad. That's polar coordinates. That's it for that part. We're not done, though, because there's an interesting relationship between polar and complex numbers. Something really, really cool, I think. So sometimes we don't have all the info. Sometimes we need to convert complex numbers to make them usable in a different way, which again, I just think is cool. So complex numbers are when we take a one-dimensional number and we give it a second dimension with the imaginary component. So real number exists on a horizontal number line. The imaginary number system is perpendicular to it. So it takes something that's one-dimensional, makes it two-dimensional, which is kind of cool, which also means it would take something that's two-dimensional, make it three-dimensional, so on and so forth, right? Well, the A in A plus BI is the horizontal distance, and the B in A plus BI is the vertical distance. That kind of reminds me of a point, x comma y, right? Just in this case, A comma B. Interesting. So if I wanted to describe this imaginary number in terms of a complex number, I can use very similar things. That might be foreshadowing, but very interesting. First things first, though, absolute value. Like, how do I take the absolute value? How do I find the distance from 0, 0, the origin, to an imaginary number? Normally, when you take the absolute value of a number, it pops out the positive version of that number. So if it's already positive, it stays the same. If it's negative, it makes it positive, right? That's what you've been taught. But absolute value is the distance from 0. That's the true definition, which is why that interesting relationship occurs. For us, and the idea of absolute value, with that distance factor in mind, the absolute value of a complex number is going to be its distance from the origin. So we need to use the distance formula. So the absolute value of a complex number, in this case we're going to call that complex number z. The absolute value of z is equal to the distance formula using the real component and the imaginary component without the I. So we're not throwing any i's in there. Very interesting. So let's graph an imaginary number on the imaginary plane. We've done this before. Hopefully we've done this before. And then let's find its absolute value. So 3 plus 4i means we have 3 on the real axis and 4 on the imaginary axis. So this would be z. And if I want to find its distance from 0, its absolute value, well, if z is equal to 3 plus 4i, then the absolute value of z is equal to the square root of 3 squared plus 4 squared. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, square root of 25 is 5. So the absolute value of z is equal to 5. Not bad. How do we express points as imaginary numbers, or complex numbers, really? We take the real component, so 1, 2, 3, 4 to the left would be a -4, so z is equal to, and then we take the imaginary component, which is 1, 2, 3 down, so minus 3i, all fine and dandy. If I want to find the absolute value of this one, we would do the same kind of thing. So we would have -4 squared plus -3 squared. And if you notice, we're using the same numbers and we're squaring them. So the absolute value of this imaginary number is also 5. Very cool. So I foreshadowed it before, but we can convert rectangular imaginary numbers to polar imaginary numbers. They have polar forms, which is very, very similar to this a plus bi. It's just a is now r cosine theta, and b is r sine theta. That sounds familiar. And it comes from what we've just done. Before, the x-coordinate, we'll define to convert the x-coordinate from polar, we would do r cosine theta for the x-coordinate. And the y-component, which is the imaginary part here, we found before using r sine theta. Same idea. So polar complex numbers take the form of r cosine theta plus I r sine theta. Or you can factor out the r and just have r times cosine theta plus I sine theta. Very cool. How do we convert? We convert the exact same ways we did before. So here is my analogy. We had x and y comparing to a plus bi. Now we have r and theta. So again, we have these relationships that we've already established, and we can already see the connection to. So they're not just random, pulled out of nowhere. They have a connection to what we've already done, which I, again, think is really cool. So let's convert. So here we have a and b. So to find the r is equal to, well, instead of x squared plus y squared, we're going to do a squared plus b squared. So in this case, r is equal to, well, r is equal to the square root of -3 squared plus the square root of 7 squared. Square root of 7 squared is 7. Remember that the square and the square root are inverses. They would cancel each other out. And the -3 squared is 9, so 9 plus 7 is 16. Square root of 16 is 4, so the radius here is 4. Great. How do we find the angle? Well, the angle we would find in the exact same way. We're going to use the tangent, inverse tangent of, remember the elevation is with the imaginary component, so we will have b over a. So instead of y over x, it's going to be b over a. Again, we have the same restrictions that this only works for quadrant 1 and quadrant 4. So we have to add pi if we're in quadrant 2 or 3. And if we're in quadrant 4, we really have to add 2 pi to make sure it's positive. Here we are to the left and up. We're in quadrant 2. So we're going to have to add pi to our answer. So to find the angle, we have to do the inverse tangent of, in this case, the square root of 7 divided by 3. Let's figure out what that is. Oh, -3. So we go to our fancy calculator, and we do the inverse tangent of the square root of 7. So the square root is second x squared, 7. Move out, divide by -3. Again, this gives us quadrant 4 stuff. We don't want quadrant 4 stuff. We want quadrant 2 stuff. So we need to add pi to it. So here's our angle. So 2.419. So how do we write this? Again, we have to be careful. We can't just write r comma theta. We can't just do that. We have to write it in the complex form, which again is r cosine theta plus I r sine theta. So writing that out, we would have 4, and then we want to do cosine of 2.419 plus, and when you write an imaginary number, you always put the I at the end, so we're going to do that here. We're going to do 4I sine of 2.419. Not too bad. A little weird, yes, but not that bad. Let's do it with this one here. So I don't have to write out a lot of this extra stuff here. So we know that r is equal to the square root of, remember this has a coefficient of 1, so -1, 2 squared plus -1 squared. 2 squared is 4 plus -1 squared is 1, so the square root of 5 is r. Interesting. What quadrant are we in? We are to the right and down, so we are in quadrant 4, so we're going to want to add 2 pi to our answer. But let's start with the tangent inverse of the y component over the x component. I feel... No, that's not a special one. It looked like a special one. If it was sine or cosine, it would be. Inverse tangent of negative 1/2. Perfect. We want it between 0 and 2 pi, so we're going to add 2 pi to it. Let's do that. And here we are. So we have, that is 5.8182, I guess, right? 82. So this in polar form would be, let's factor it out this time, the square root of 5 times the cosine of 5.82 plus I sine of 5.82. So, not that bad, right? Converting the other way is actually quite simple. All you really need to do is figure out what 3 cosine pi over 3 is, and that is your A, and 3 sine of pi over 3 is your B. Really not that bad to go the other way. So let's draw the triangle, because again, these are special angles. Let's use their special triangles. So pi over 3 would be the middle, so this would be 1 root 3, 2. Cosine would be 1/2, so this would be 3/2, plus sine would be root 3 over 2, so it would be 3 root 3 over 2I. Not bad, right? Super not bad. Here we have quadrant angles, which is interesting. So 3 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, we are down, which means we are using the point 0, -1. So cosine would be the x-coordinate, so this would just be 0. And then the y-coordinate would be -1, so this is -1 times 4, so -4i plus -4i, so we can just make that -4i. So, not bad at all. If you have any questions, please make sure you ask. Otherwise, I'll see you in the next video.